The topic this week is geometrical optics. We've studied electromagnetic waves as an effect of electromagnetism, and we've seen how that includes light, all the different kinds of light, in particular visible light. And now optics is the science and technology of light. Geometrical optics, well, it's chapter 21. It's got a number of sections. The two most important phenomena for this chapter will be reflection and refraction. All right, so geometrical optics. There's another branch of optics called wave optics, which will be for next week, chapter 22. But this week it's geometrical optics. Electromagnetic waves, including visible light, propagate in straight lines in any uniform medium. The wave speed is v, which is c divided by n, where c is the speed of light in vacuum and n is the index of refraction of the medium. Now, where the medium has a spatial variation, the light waves may change in direction and in wavelength and in velocity. In fact, that's what we're going to be studying in geometrical optics, how light changes its direction and wavelength and velocity. And to analyze the propagation of light, just the motion of the light in its direction, we use what's called ray tracing. And that's the subject of chapter 21. So we'll say if there's a light wave traveling through a uniform medium, let's say through glass in some direction, well, for this week, we won't consider the wave oscillations. For this week, we'll just replace that wave by a ray, an arrow. So it shows in what direction is the light moving. So that's what we call a ray. The first phenomenon we want to consider is reflection. That occurs where light hits a discontinuity between two different media. So I might have light in some region where the index of refraction is N1, hitting a boundary surface to another medium where the index of refraction is N2, and that's a discontinuity between the optical properties, the indices of refraction. And several things can happen. It can reflect, or it can pass into the other medium. That's called refraction. So this is reflection. Refraction is when the light goes into the second material. And also it may be absorbed. The light may be absorbed. Energy is conserved, but light energy can be transferred from the electromagnetic fields into the material, the atoms or molecules that make up the material. And that's absorption. Now, the ideal reflection is a mirror, an ideal mirror. In an ideal mirror, like a piece of highly polished silver, there's only reflection. For a dielectric surface, like a polished surface of glass, there will be reflection and there will also be refraction. In other words, some of the light will pass into the glass. As you know, glass is transparent. It's not 100% transparent because part of the light that hits it is reflected. But glass doesn't really absorb light. Now, reflection is described by the law of equal angles. In reflection at a smooth surface, the angle of reflection is equal to the angle of incidence. That's called specular reflection or mirror reflection. I have the incident ray. Now this ray represents a whole wave. So maybe put this in a different color. This ray is supposed to represent a wave. So it's got crests and troughs. It makes a ray. It makes a beam. But if I'm only interested in the direction of propagation, I don't have to take into account those oscillations, the wave fronts. And similarly, the reflected wave has crests and troughs, positions, planes where the electric field is pointing out towards you, planes where the electric field is pointing away from you, then planes where the electric field is pointing outward, out of the page, into the page. Light is a transverse wave. So the electric field is oscillating back and forth, so is the magnetic field. And we have these planar wave fronts. But that's not ray tracing. For ray tracing, I only need to look at the direction of propagation. And the law of equal angles says theta reflected is equal to theta incident. We measure these angles relative to the normal to the surface. That's the line perpendicular to the surface. So here's the surface, the discontinuity. Here's the direction perpendicular to the surface. We can say the surface is the xy plane, then the normal is in the z direction. This is how we measure the incident angle. It's the angle between the incident ray and the normal. And then the law of equal angles says the reflected angle, again measured relative to the normal direction, is the same. They're equal. Now, when light reflects from a mirror, you get an image. You see a copy of whatever the form of the light is that hits the mirror. Suppose you're looking at yourself in the mirror. Light reflecting from your face hits the mirror, reflects off the mirror, and comes back into your eyes. So, of course, the light is a reflected light. But let's say you're looking at yourself in a mirror, there'll be light from the room that reflects off your face, hits the mirror, reflects back into your eye. Well, not only into your eye, it reflects back in all directions, but in particular, it reflects back into your eye. So you will see an image of your face. Because of the law of equal angles, the image will look just exactly like your face. In other words, it won't be distorted. So that's a plane mirror. a mirror which is just a plane surface. So for plane mirrors, the image is behind the mirror the same distance as the object is in front of the mirror. So if your face is 3 feet from the mirror, you'll see your face as if it was 3 feet behind the mirror. Of course, there isn't really anything behind the mirror. The mirror is probably mounted on a wall, so there's nothing behind the mirror. The light that you're looking at is coming from the surface of the mirror. But it looks exactly like an exact copy of you is standing 6 feet in front of you. You're 3 feet in front of the mirror. Your image is 3 feet behind the mirror. So your image is 6 feet away from you. So that's plane mirrors. That's the simplest case. And you'll have some law and kappa problems where you have to analyze reflections in a plane mirror. That's the simplest case. But where things get interesting is if you have spherical mirrors, curved mirrors. You know, maybe you've been at one of these circus sideshows where they have distorted mirrors, and you go in and you look at your reflection and it doesn't look like you at all. It looks all distorted. Well, that's because the mirror is not flat. It's not a plane. It's curved. Now, what we'll analyze in this chapter is spherical mirrors. The surface of the mirror is a portion of a surface of a sphere. And there are two kinds of spherical mirrors. There are concave mirrors. That's where the reflective surface is the inner surface of the sphere, or the spherical section, spherical arc, solid arc. Now let's see what happens. First of all, the characteristic of a spherical mirror, or more precisely, a parabolic mirror, but as long as the mirror is approximately spherical, it's about the same as a parabolic mirror, is that there's a focal length. And what happens, all right, so there's a focal length. We'll call that F. Now you have some object. Let's say you're looking at yourself in a spherical mirror. Well, I can't draw a picture of yourself, so I'll draw a picture of an arrow. So this is you. This object, this arrow, that's you. The light hits the mirror and reflects back and forms an image. But it's not like a plane mirror where the image is exactly like the object. If I had a plane mirror, I'd have an image over here. It's not real. There's nothing really back behind the mirror. There's nothing behind the mirror, but it's the position of the image. That's called a virtual image. But in this case, it's not like that. If I trace the rays, let's trace a ray from the top of your head to the center point on the mirror. By the law of equal angles, it will come off in this direction. So the light that's coming from your hair, or let's say you're wearing a hat, the light that's coming from your hat, it's reflected from your hat, hitting the mirror at that point, the light is coming out this way. At equal angles. Now let's also consider light that's coming from your shoes to the center of the mirror. So let's suppose you have shoes with little light bulbs in them. So the light from the light bulbs will come and hit the mirror. If it hits the mirror at this point, it'll come off at equal angles. In this case, the angle of incidence is 90 degrees. So it'll come off at equal angles. So the light coming from your shoes will hit the mirror and it'll come back out this way. So you see, your shoes, the light will pass through this point. I'm not talking about the light from your shoes. I'm talking about the light from the mirror. And from your hat, the light will come through this point. And I could take any other point in your body here and analyze it similarly. The reflected light will form an image which will be like this, an upside down copy of yourself with your hat below your feet. So the image will be inverted. Now, we define several distances to analyze here. We define D0. That's the distance from the object to the center of the mirror. That's D0. That's called the object distance. No, it's not D0. It's DO for D object. Then there's DI. That's the image distance. That's the distance from the mirror to the image. So here's DI. And here's DO. And those are related to the focal length. Now we also define H0, not H0, HO for object, the height of the object. And we define HI, the height of the image. So you see we have four lengths here, D0, DI, H0, HI. And we have a fifth length, that's the focal length. And now you can relate these various things by trigonometry. This shaded in triangle is similar to this non-shaded in or light shaded in triangle. So HO divided by DO is equal to HI divided by DI. So there are various equations following from trigonometry or geometry relating these various distances. Now there's a relation between DO and DI. One over DO plus 1 over DI is 1 over F, where F is the focal length. For a spherical mirror, the focal length is equal to 1/2 of the radius of the mirror. So this is in chapter 21, equation 2. This is an equation we'll see over and over again. And the other equation is the equation for magnification. So M is called magnification. It's the ratio HI divided by HO. Now you can see in this problem, M will be less than 1 because HI is smaller than HO. So M, the magnification, may be less than 1 if something is reduced in size, but it could be greater than 1 if something is increased in size. And by the similar triangles, HI over HO is DI over DO. But there's a minus sign. And that's equation 3. The minus sign indicates that the image is inverted. You know, the top or the hat on the object is at positive y. The hat on the image is at negative y. So we say hi over ho is minus di over do. And the sign tells me that it's inverted. All right. Now this is a concave mirror. The reflection is from the inside of the sphere. It's like a little cave. You know, the light's coming into a cave and reflecting back. Here's another analysis. Part B of the figure. If we imagine a ray of light that goes not to the center of the sphere, but it goes through the focal point of the sphere, so there's a focal length, which is 1/2 the radius of the sphere. Light that goes through the focal point reflects parallel to the axis. So we have here the axis of the sphere, and light from the hat goes through the focal point, hits the sphere, and it bounces off the sphere. That's reflection. It comes out parallel. There are equal angles here. You know, there's an angle of incidence here. There's an angle of reflection here. They're equal. The definition of the focal point is that light that goes through the focal point comes off parallel to the diameter, or parallel to the axis. So, you know, this distance is the focal length, 1/2 the radius of the sphere. This distance is do. So the distance from here to here is do minus the focal length. And of course the distance from here to here is di. And by analyzing the triangles here, and you'll have to look at that in the book, you find that 1 over do plus 1 over di is 1 over f. All right, so that's the case of a concave mirror. That's called a converging mirror because light that comes this way, parallel to the surface, goes down through the focal point. So you see the light is reflected toward the axis. Well, not exactly, because down here it's reflected parallel to the axis. But light that's coming in towards the center of the sphere is reflecting off towards the central axis, or toward the focal point. Now, we also have convex mirrors. And a convex mirror is the opposite of a concave mirror. It's again a spherical mirror, but the reflecting surface is on the outside of the sphere. And a convex mirror is a diverging mirror. Light that comes in parallel to the surface reflects off at equal angles. So that's this way. So the reflected light goes away from the axis. That's diverging. So you have light coming in and light going out at these kind of angles. So the light isn't squeezed together, it's diverged apart. Now, there's a relation between DO, that's the distance from the object to the surface, and DI, that's the distance from the object, from the surface to the image. In this case, the image is on the other side of the mirror, just like if you had a plane mirror. You know, if you had a plane mirror, you'd have an object over here, and you'd have an identical image over here. Well, in the case of a convex mirror, you have an object over here, and behind the mirror, there's an image. But it's not identical. It'll have a different size, and the distance from the mirror will be different. Whereas for a plane mirror, these two different distances would be equal. All of this is because of the law of equal angles. Now here the focal point is in back of the mirror. Parallel light, let's say this ray of light, this ray of parallel light reflects from the mirror at equal angles. It reflects in the direction which you can trace back to the focal point. So here's one ray of light. It comes in parallel. It reflects directed away from the focal point. Here's another ray of light. It's coming in toward the focal point. It's directed toward the focal point. Of course, it doesn't get to the focal point because that's behind the mirror. The mirror is opaque. But it hits the surface and it comes out parallel to the axis. So that's ideally for a parabolic mirror, but also for a spherical mirror approximately. Okay, now here you see the image is upright because the light coming from the hat, the top of the arrow, is coming off in this direction. So this is light coming from the hat. And it's coming off in this direction. So this is light coming from the hat. Here, light from the hat reflected at this point on the sphere and came off in this direction. Here, light from the hat hit this point on the mirror and came off in this direction. So these are both rays of light coming from the hat. Now, if you trace them back to where they intersect, that will be the image of the hat. So this point is the image of the hat, and this point is the image of the feet. And any place in between the feet and the hat, you get a similar point making up the full image of an arrow. But you see, the hat is on the same side of the axis as in the case of the object. So in this case, the image is pointing upward, same direction as the object. The focal length is, now, this same equation is true. But the focal length here is negative. For a concave mirror, the focal length is r over 2, where r is the radius of the mirror, r over 2. For a concave mirror, the focal length is positive. It's r over 2. But for a convex mirror, the focal length is minus r over 2. Negative r over 2. That's because for a convex mirror, the focal point is on the other side of the mirror, in the negative region. But now this same equation will hold true for the convex mirror. It's just that in the case of the convex mirror, I have to put here 1 over minus r over 2. For the convex mirror, f will be a negative number, or a negative length. So the focal length is negative because the focal point is on the other side of the mirror from the incident light. Here's a figure which shows how the object relates to the image. Image formation in a convex mirror, the image is always virtual. That means it's on the back side of the mirror. Upright, it's pointing in the same direction as the object, and reduced in size. And once again, we have these equations. 1 over dO plus 1 over di is 1 over f. And again, we have the equation m is hi over ho. That's just the definition of magnification. But m is minus di over do. Exactly the same as here. So you get the same equations. But in the case of a convex mirror, f is taken as negative, the distance from the mirror to the point. Here's an example of a convex mirror. Here's an example of a convex mirror. It's used as the outside rear view mirror in a car or in a truck or in an SUV. It has a little warning on it. It says, objects in the mirror are closer than they appear. The phrase, object in the mirror are closer than they appear, is a safety warning that's required for passenger side mirrors on motor vehicles in many places such as the US, Canada, etc., etc., etc. These mirrors' convexity give them a large field of view, but it makes objects appear smaller. You know, just like in the other slide, the image size was small. Well, you know, this motorcycle is not as small as it looks, because you're not really looking at the motorcycle. You're looking at the light reflected from the motorcycle, which is behind you. The motorcycle's behind your car. The light from the motorcycle is reflecting off the convex mirror. You see an image on the other side of the mirror. It's a virtual image, and it's reduced in size. So the object is actually closer than it appears. All right, that was reflection. By tracing the rays of light, the direction of propagation, with the law of equal angles, we can determine the image formed when light reflects from a mirror surface. Now we come to refraction. The technology that goes along with refraction is the technology of lenses. But let's start with the physical phenomenon of refraction. Let's suppose we have incident light on a surface between two media. Medium 1 has some index of refraction N1. Medium 2 has some different index of refraction N2. So there's a discontinuity in the optical properties at this point. If we call the surface here the xy plane, then this would be the point z equals 0. And the normal is the z-axis. Remember, we measure the angle of incidence. It's the angle between the incident ray, that the direction of that wave, with respect to the normal. So that's theta 1, angle of incidence. Now there will be reflection. This might be air and glass. Medium 1 might be air, medium 2 might be glass, or medium 2 might be water. You know, if you had a very still lake, you could have the reflection of the sunlight from the lake surface. Now glass or water, those are transparent. So you might think, well, the light will just go down into that material. But that's not right. Part of it is reflected. So, as you know, you can look at yourself in a lake. If you bend over and look in the surface of a lake, you can see a reflection of yourself. That shows that the light is reflecting from the surface. The same is true of glass. So there'll be this incident ray. Some percentage of the energy in that electromagnetic wave will be reflected off the surface, and it will obey the law of equal angles. So this is the angle of incidence. This is the angle of reflection. It's the same as the angle of incidence. It's theta 1. But since medium 2 is transparent, some of the light will go into medium 2. But it will change its direction at the surface. And so the ray, which gives the direction, will not be in the same direction as the incident ray. It'll be bent. If light goes from a low optical density, like air, into a high optical density, like glass, the refracted ray is bent toward the normal. You could have the light going the other direction. You could have a light bulb down here. And then you would have light going from the glass into the air. You would have the very same picture, except the direction of the arrows would be reversed. The rays would be in the other direction. So in that case, a ray of light incident from a dense medium into a less dense medium will be bent away from the normal. All right, now we'll call the angle of refraction theta 2. All right, so here's a picture from the book. Quantities in Snell's law. What is Snell's law? Well, Snell's law describes the relation between theta 2 and theta 1. It tells you how much change in direction occurs when light passes through the surface of a dielectric material. So here's Snell's law. For a refraction at a surface bounding two transparent materials, n1 sine theta 1 is equal to n2 sine theta 2. n1 is the index of refraction of the first medium. n2 is the index of refraction of the second medium. Let's suppose we have light from air into water. The index of refraction of air is pretty close to 1. The index of refraction of water is 1.33. It's a little larger than 1. So 1 times sine theta 1 is 1.33 times sine theta 2. That means theta 2 must be smaller than theta 1. In other words, it's like in this picture. The refracted ray is bent towards the normal because n2 is larger than n1. And the amount of bending is given by Snell's law. n1 sine theta 1 is n2 sine theta 2. For n1 less than n2, the refracted wave bends towards the normal because the sine of the angle is less than the sine of the incident angle. But for the other way around, n1 greater than n2, the refracted wave bends away from the normal. That would be like if I had a light bulb down here. The light would hit the surface and be bent away from the normal. Now, why is this true? This was proven by Mr. Snell, who I guess was Dutch. Probably in the probably in the 17th century, so many hundreds of years ago. Mr. Snell figured this out. There was also a Frenchman, Descartes. Descartes also determined this relationship by mathematical analysis. So the French call this Descartes' law, but everybody else in the world calls it Snell's law. And here's the proof. There's a little geometrical proof. Refraction occurs because of different wave speeds and hence wavelengths in different media. The speed of a wave is the speed in vacuum divided by the index of refraction. So the speed of a wave in a material is less than the speed of a wave in vacuum. By the factor of the index of refraction. Now, when the wave hits the material, the frequency does not change. However, the wavelength does change because the speed of the wave changes. Because remember, the speed of a wave is the frequency times the wavelength. One wavelength travels a distance v in 1 second, or in one period. The frequency is 1 over the period. So the wavelength and the velocity are proportional because F is the same in both materials. Ultimately, that comes from electricity and magnetism. The electric and magnetic fields have to remain continuous at this boundary. And so they're alternating, they're oscillating. But they have to be oscillating at the same frequency in order to remain always continuous at the surface. So they have to have the same frequency. But that means as the wave propagates away into the material, the wavelength will be different for the two materials. So here will be a low index of refraction. Here will be a high index of refraction. So this might be air and water. These are the wave crests. Well, this wave is traveling faster than this one because this has a small index of refraction. This has a larger index of refraction. Larger the index of refraction, the slower the wave is traveling. So the wave here is traveling slower. So the wave crests kind of get piled up on each other as it propagates away from the surface, and they end up closer together. So you have a smaller wavelength. And by analyzing, well, in particular, this triangle, these two triangles have the same hypotenuse. These two triangles have the same hypotenuse. Their short sides are the wavelengths. So this wavelength is lambda 1, this wavelength is lambda 2. And by analyzing, well, that determines the angles. The sine of theta is lambda over the hypotenuse. Sine of theta 2 is lambda 2 over the hypotenuse. So the sine of theta 1 divided by the sine of theta 2 will be lambda 1 divided by lambda 2. But the ratio of the wavelengths are proportional to velocity. The velocity is inversely proportional to the index of refraction. So the ratio of the wavelengths will be inversely the ratio of the indices of refraction. So sine theta 1 over sine theta 2 will be n2 divided by n1. Or we write it this way, Snell's law. Now something interesting can happen if n1 is greater than n2. If you have light coming from a dense material like glass into a less dense material like air, something interesting can happen for n1 greater than n2. which is called total internal reflection. If theta 1 is greater than the arc sine of n2 over n1, and of course this is only well defined if n2 is the smaller one, so n1 is larger than n2, so n1 is larger than n2. This is a particular angle which is called the critical angle. And if theta 1 is larger than the critical angle, then there will be no reflection. There will be only refraction. So this is called total internal reflection. All of the incident light reflects back into the material. But it only happens if the incident light is coming in a dense material. In other words, if you have light inside glass, like let's suppose you had a light bulb over here. That would be at a large angle of incidence. This would be the angle of incidence, this angle. If the angle of incidence is, say, 80 degrees, all of the light will be reflected. It'll obey the law of reflection, law of equal angles. None of the light will get out of the glass. So the light is trapped in the glass. That's called total internal reflection. And here's an example of refraction. Observing a fish underwater. So here's air above the surface and water below the surface. And so you're looking in the surface of a lake. Here's your eye. Here's a fish underneath the water. Now a fish doesn't emit light, but it does reflect light. So there's light coming from the fish. Here's the fish. Here's the fish. Light is reflecting from the fish. It's coming up and hitting the surface. It's bent away from the normal. So it's bent in this direction. And if your eye is there, you'll see the fish. But the fish won't look like it's here. The fish will look like it's here. This is the apparent position of the fish. Because the light that you see is coming from this point, but it looks like it's coming from this point. You know, if you imagine, your brain can't do Snell's law while you're looking under the surface of the water. Your brain is just going to interpret the direction of that light as being the direction of the source. And your brain is going to say the source is about here. So when you observe a fish underwater, the fish appears to be closer to the surface than it really is. That's an example of refraction. Probably a more familiar thing would be, suppose you're standing in a swimming pool. So you're standing in a swimming pool and you're looking at your feet. Your legs seem to be much shorter than they really are. Your feet seem to be closer to your eye than they really are. So that's an example where, since light doesn't travel in straight lines, not when it goes through a discontinuity, your perception is thrown off. So that's the example of observing a fish underwater. Here's a picture which shows total internal reflection in an optical fiber. This is how optical fibers work. You know, if you're getting your information to your laptop from an optical fiber, if you have optical fiber carrying signals into your room, light is carrying the signal. Visible light is carrying the signal. It's carrying the signal along this fiber, which is a transparent piece of some kind of plastic material. Light propagating.
Okay.
Light propagating in a fiber optic cable undergoes total internal reflection when it hits the surface of the cable. And so it travels down the cable from, the transmitter to the receiver. So that's an example of total internal reflection. Now, just like there's image formation in mirrors, there's also image formation in lenses. A lens is a piece of glass in a certain shape, and light passes through it because it's transparent. But when light encounters the surface, it undergoes refraction. Also reflection, but we're not interested in the reflection. We're interested in the light that goes through the lens. So whenever light hits a surface between two different materials, there's refraction. And refraction is given by Snell's law, the direction of the rays. Now, there are many cases. You can have convex or concave lenses. So here's a picture. This is a convex lens. And its shape is designed in such a way that a parallel ray that is parallel to the axis of the lens will be bent by refraction and go through a focal point. So rays converge at the focal point. Parallel rays. Parallel rays enter the lens, are bent by refraction twice, once at each surface, and a group of parallel rays all go through the same point, which is called the focal point. So that's called a convergent lens because the light on the other side of the lens is converging to a point. Well, that's one kind of lens. That's a convex lens. But then there is another kind of lens which is called a concave lens. Again, it's concave. It's shaped like a cave. This is a divergent lens, or a diverging lens. Parallel rays, parallel to the axis of the lens, as they pass through the lens, they diverge. They're bent, but they're not bent together. They're not converging. They're bent apart. They're diverging. Now, if you trace those outgoing rays back, if the concave lens is correctly ground to the right shape, if you trace those diverging rays back, they'll all go back to one point. So again, there's a focal point. But it's a focal point on this side of the lens. It's a focal point on the side of the lens where the incident rays are coming from. So there's actually no light coming from the focal point. All the light is over here. But if you trace these rays back, they would appear to be coming from a point. Now, you can have an object which is close to the lens, in either case, or you can have an object which is far away from the lens, in either case. You could measure the distance relative to the focal length So this will be the focal length for a convex lens. You could have an object here, closer to the lens than the focal length. Or you could have an object way out here, farther away from the lens. And similarly for a concave lens. So here we got two possibilities, and for each of those two possibilities we have two possibilities. So that's altogether four possibilities. Now, depending on which of those four states are created, you may have upright images or inverted images. The image, if you put a source of light here as the object, so there's O, the object, you may have an upright image or an upside down image, an inverted image. And you may have a real image or a virtual image. So, there's sort of many possibilities, numerous cases. And they can all be analyzed by ray tracing techniques. And I won't really have time to go over that in the Zoom, in the screencast here. You'll just have to read it in section 4. Now, just as we had for reflections, we'll be interested in the geometry. So we might have some distance DO. The distance from the object to the center of the lens. And we might have a distance DI to the image. From the center of the lens to the image. Well, once again, we have this equation. 1 over dO plus 1 over dI is 1 over F. And that's equation 7, chapter 21. And again, we have the magnification of the image, the ratio of the size of the image to the size of the object, is again negative dI over dO. So we have these equations, and it looks very simple, but it's deceptive. It's not as simple as it looks. You have these two equations, but you have to be careful about the signs. And we already saw that in the case of spherical mirrors. Sometimes the sign of the focal length is negative. Well, for a diverging lens, the sign of the focal length is negative. Whereas for a converging, like a convex lens, the sign of the focal length is positive. So, be careful. You'll be applying these two equations on the Lawn-Kappa problems. But you'll have to go back and read section 4 carefully and make some notes. Take notes. When do you need a negative sign? When do you need a positive sign? Sometimes a distance might be negative. That might indicate either a real or a virtual image. A real image might be positive, a virtual image might be negative. So, as I say, there are many possibilities. And the only real way to grasp all this is to read section 4 and take notes. Now, before I end this screencast, I want to mention one more phenomenon, optical phenomenon, called dispersion. The index of refraction of a transparent material, N, so remember N, the index of refraction, is the speed of light in vacuum divided by the speed of light in the material. N is always greater than 1. Now, N depends on the material. And all material is atomic. All matter is atomic. Different atoms react to light in different ways. And so N is not just a constant. It's different for different materials, and it's also different for different frequencies of light. So here's a picture from the book. It's figure 21, which shows the index of refraction for 1, 2, 3, 4, 5, 6 different kinds of transparent materials. Different kinds of glass, quartz, fluorite, some crystal. And you see, well, the index of refraction is always greater than 1. For all of these 6 different materials, it's sort of on the order of 1.5, maybe a little bit bigger, maybe a little bit smaller. But it also depends on the frequency of the light. You know, it's really the interaction of the electric field in the electromagnetic wave with the electrons in the atoms. And the different materials have different kinds of atoms and molecules. Now, there's a relationship between wavelength of an electromagnetic wave and frequency. Wavelength times frequency is the speed of light. In the material, that would be V, divided by the frequency. So you see, if N depends on the frequency, N is a function of frequency, then N depends on the wavelength. And the wavelength of light, different wavelengths correspond to different colors. Unless you're colorblind, but if you're not colorblind, you can perceive different wavelengths as different colors. So the range of wavelengths for visible light is something like 400 nanometers. Those are the short wavelengths. That's like blue and violet. 400 nanometers, up to about 700 nanometers. Those are the wavelengths that correspond to red light. So I can make a graph of the index of refraction as a function of the wavelength. This will be the wavelength in vacuum, not the wavelength in the material. But I can convert back and forth from the wavelength in the material to the wavelength in vacuum. The ratio of the wavelength in material to the wavelength in vacuum is just the index of refraction. But to keep track of all of the different materials, they'll all have different transformations of wavelength. So let's just plot the wavelength in vacuum. Then what's the index of refraction? Well, you see there's some wavelength dependence. It's not terribly strong, but this is why a glass prism separates white light into all the colors. White light is a mixture of all the different wavelengths from 400 to 700 nanometers. White light is not some kind of pure light. White light is sort of the opposite of pure light. White light is a mixture of all different colors. Now, if you pass white light through a prism, by refraction, different colors will be diverted by different angles, because the angle depends on the index of refraction, and the index of refraction depends on the wavelength. So you'll have red light, long wavelengths, will be bent through a different angle than blue light or violet light. So a prism, white light passing through a prism, separates, when it comes out of the prism, into the colors. And of course, it's not only for glass, it's also for water. Water has a frequency dependence, or equivalently a wavelength dependence, of the index of refraction. And that's how a rainbow is formed. A rainbow is the reflection of light through a drop of water. So you have in the atmosphere a drop of water. You have sunlight coming into this drop of water, reflecting off the back surface, and coming down towards the ground. So here's sunlight coming from the sun, going through this drop of water, reflecting off the back surface, because at every surface it reflects a little bit. You know, at this surface there's some reflection and some refraction. At this surface there's some reflection and some refraction. Whenever there's reflection, there's the law of equal angles. Whenever there's refraction, there's Snell's law. Those angles that come out of Snell's law depend on the index of refraction. And the index of refraction varies with the color. So you'll have your eye down here. So here's your eye. Well, eyes aren't usually yellow. Let's make the eye blue. Eyes are blue. So here's your eye. And here's the light from the sun. Now, what color is the sun? The sun is white, because the sun emits light of all the colors. So I draw it here as yellow because I can't draw white on a white background, so I'll put it in yellow, but it's really white. In other words, it's a mixture of all the colors. And when the colors come out of the drop of water, they're separated. They're separated. So on one side, they'll be red. I guess that's the upper side. So on the upper side, there'll be red light. That's the red component of sunlight. And on the other side, there'll be blue light. So there's the blue component of the sunlight. That's the fraction of the sunlight that's blue, a fraction of the sunlight that's red. And so you get a separation of the colors. You're looking at back here, you see back here a rainbow. You know, you trace the direction of the light back, you'll see it as a rainbow back here. So that's called dispersion. It's dispersion. It's spreading out the frequencies. Or I could say it's spreading out the wavelengths, because frequency and wavelength are related. Or I could say it's spreading out the colors, because the colors and the wavelengths are related. My father was colorblind. He was red-green colorblind. He couldn't really see a difference between red and green. Made it a little difficult to drive a car. I think as a few percent of men are colorblind. Not very many women are colorblind. I never asked my father. I should have asked my father. I never asked my father, what does a rainbow look like to you? All right, so that completes the screencast for chapter 21. There'll be quite a bit you'll have to read in the textbook to do the law and kappa problems. The law and kappa problems will have questions about Snell's law, reflection and refraction, reflection from mirrors, refraction through lenses. So I would say read through chapter 21 and then start doing the law and kappa exercises.